Hello, good morning, everyone. Welcome to this seminar hosted by the Bioengineering Department and the Communications and Sensing. Today, we are really honored to have Dr. Abdullah Abdulhameed with us. Dr. Abdullah, mashallah, finished his master and PhD from Malaysia, I think like 4 years ago.
3 years.
3 years ago, yeah. So he's, mashallah, engaged with many projects when it comes to writing, implementation, very, mashallah, active, even in teaching in our department, and like shining star in KFUPM here. Today, inshallah, he will talk to us about application of controlled electric field in bioengineering and bioparticle manipulation. Without further ado, please, Dr. Abdullah, the floor is yours.
Assalamu alaikum. Good morning. Thanks to Prof. Ibrahim for your nice introduction. So today, my talk will be about the application of controlled electric field in bioengineering and biomanipulation. Okay, so basically, before I go deep into the content of this talk, I will talk about what is the outlines that I will mention. First, controlled electric field and what's controlled electric field. Also, usually within electric field, there will be a generation of forces, which called electrokinetic force. Also, I will talk about one specific force, which called the dielectrophoresis. I will shortcut with DEB. And then I will go into the application and how we can apply these forces into the bioengineering and bioparticles manipulation. After that, I will conclude with what is the challenges and also what's the advances in this method. Okay, so again, before I go into deep in this talk, let me break down the title. So first, controlled electric field. We know that the electric field, if we can see it, it will look like lines, maybe parallel lines or maybe twisted lines. So how we can control it? There is basically three things you can utilize or you can use to control your electric field or to generate it in a way that to do a certain purpose or a certain task. There is three things. First, the electrode geometry, which is number one. So you can control your electric field by designing electrode in a specific way. Also, you have the signal source, and the signal sources can be AC, can be a DC, and also can be a different shape, for example, sinusoidal wave. And also we have the medium, which is the medium that you will put between your electrodes. So also the medium and the properties of the medium can be used to control your electric field. Okay, so the second term in the title is the electrokinetic forces. It is actually comes from the name here, electrokinetics. Electro means that it comes from electrical power or electrical source, and then it cause or make mechanical change. For example, you apply electric field, and then the result, there will be a motion or a movement of certain particle. What the types or the different types of electrokinetic force? We have here a few examples. For example, the electrode deposition. Maybe a lot of you heard about this one. It is we studied in the secondary school, actually, when we learned how to coat spoon with silver. Also, we have the electrophoresis. This one also very common term in biology. We use it for the DNA or RNA fragmentation. Also, we have the dielectrophorsis, which will be the more focus for this talk in this force. Also, we have another thing or another force called the electroosmotic or electroosmosis, which is also another force that can be generated within the medium due to apply of electric field. Okay, so the last term in the title is particle manipulation. What is particle manipulation? Manipulate means that you have a particle or you have, let us say, a molecule, and then you do kind of manipulation. For example, assembly, you assemble them from one place to another place. You can do some kind of sorting, isolation. Also, you can do separation. Let's say you have two particles mixed, let's say two types of bacteria or two types of blood cell mixed together. So how can you separate them? Only by applying electric field. And alignment, also another type of manipulation. Alignment, usually if your bioparticle is not spherical, let's say you have rod-shaped particle or you have some kind of molecule, long molecule. So how can you align? You align your molecule across electrodes, for example. Okay, so now we know the title. We break down the title and I will go now in more details into these things that I just explained. First, we start with the electrode. Okay, you can see here we have different types of electrodes, and we can see the electric field that generated between the electrodes is different. For example, this is actually a pair of electrodes. We have here the rectangular, we have here like triangle-shaped electrodes, and also we have here a round-shaped electrode. We can see a different shape of electrode, the electric field will be a little bit different. For example, here the intensity of the electric field is quite high. But for the triangular electrodes, the intensity will be only at the tip. While for the round electrode, the intensity or the field will look like that when you coming close to the center, the electric field will increase. Again, here, if we have interdigitated electrode, which are electrodes actually into each other, something like this, this is side view. For the IDE electrode, if we have cylindrical IDE, also we can see the electric field will be different from if we have plate IDE electrodes, which usually will be like planar electrodes. So different shape, different geometry will give us different electric field. Okay, so now I will go again into what if the electrode actually not the same. The positive electrode and the negative electrode, for example, not in the same size or the same shape. This one, they are two parallel. Also, the size is same. We can see here the electric field is actually uniform, which means that the line is actually parallel to each other. But what if we reduce, for example, the size of the positive electrode, so it will look like small compared to the negative electrode? In this case, we can see here the electric field lines maybe parallel in somehow, but they become here more intense at the smaller electrode. While at the bigger electrode, which is the negative in this case, the spacing between each line and another line is wider compared to the positive electrode. So this field is called non-uniform electric field. This one is uniform, but this one is non-uniform. Also, if we have like similar plate IDE, but we look them from the side view, and this is from the top view. From the side view, you can see the line here also, they are not uniform. Okay, so for example, this line is smaller than the other line. This one can be straight, but this one looks like half cycle. But from the top view, if we look at this planar electrode from the top, it will look like uniform. So and somehow we can say that we can have both uniform and non-uniform at the same time. Okay, so this is for the electrode, which is actually one part of the components that can be used to control your electric field. So what other components or what other parameters we can use? Of course, the material of electrodes make difference. For example, what type of electrode you are using. For example, are you using gold electrodes, or maybe you are using ITO electrodes, also will make difference. But the other two components is the medium and also the supplied signal. For the medium, as I mentioned before, medium is what actually you place between the two electrodes. Okay, so either like parallel electrodes or just you drop one, for example, droplet on the top of electrode. This is your medium, and your medium usually will contain your particles. So we can say here the electrical properties of your medium, like for example, what is the conductivity, what is the permittivity of your medium will make difference. Also, the thermal properties, because we know that on some medium it might generate heat different from other medium. So this also will make difference. The last component, which is the supplied electric signal, because usually to generate electric field, what do you need? You need an electric field generator, for example, if you want to generate an AC, or you can just use DC supply if you want to use a DC. So the amplitude, the frequency, the shape, the duration, the time you apply, all this will make difference also to control your electric field. So let's now say we have a controlled electric field, then what? Okay, so now you have a controlled electric field within a system. This electric field actually will generate force. The force will be generated within the medium. So now I will go into what is these forces and how we can apply them, for example, in bioengineering application, and also what is the advantages and disadvantages of this force. Okay, so I will start first with the electrode deposition. As I said earlier, the electrode deposition, most of us know this one since secondary school. We know how to coat some metal with, for example, silver by using parallel electrode, and then we apply a DC across these two electrodes. So, for example, the electrode deposition actually movement of ions. In this case, ions will move, not particles. Okay, ions, and also usually will DC power. And also the electric field will be generated here is uniform. So the lines will be parallel to each other. And also usually one of the applications they use in metal coating and also on biocompatible electrodes. In some cases that, especially the, metal electrodes, for example, like silver, like gold, they actually is quite compatible electrodes. Also, there is another application of coating polymer electrodes printed on hydrogel. Hydrogel also have a lot of application in bioengineering. So in some cases that we can pour our hydrogel and then we can apply electric field so that it will happen something like electrode deposition on the other side of the hydrogel. And then we can apply the electropolymerization, which is actually one type of the electrode deposition. And then we can get different type of electrodes. So this is like one of the forces, which actually this is more common in our labs. So the second force, which is the electrophoresis. Electrophoresis is different from the previous one because it is the movement of charged particles. Okay, so now it is not movement of ions, it is a movement of charged particle. So it can be powered by DC or AC, both can work. Also, again, it uses same uniform electric field. So electric field here is also uniform. Application of this, maybe we have actually gel electrophoresis, which is one type of analysis that we drop DNA or RNA fragmentation here, and then we apply a specific electric, and we can see that, for example, it also can be used for proteins. It will look like some fragmentation here, and then can we decide what type of, or actually what is the type of DNA or RNA. Also, in another way that usually the particle or the charged particle requires some kind of functionalization or treatment, that we need to do some treatment before we apply the electric field. So this is the electrophoresis, which is, I will not go deep here, but the second one or the following force. The following force is also called electroosmosis or electrothermal. This one also one of the methods or one of the mechanisms that have a lot of application also. So let me first introduce the force and how it is different from the previous one. First, it is movement of a liquid, which means that usually the liquid will contain particle for sure. But the mechanism of this force usually is the liquid that it will move due to some kind of heat. For example, the temperature near the electrode will be higher than the temperature on the top of your droplet. It will cause some kind of medium circulation. And the medium circulation will take the particle from down here to the top and will cause something like vortex. So it is also DC and AC powered, so you can use an AC or DC electric field. The electric field here can be also either uniform or either non-uniform, because both can be there. Okay, so what is the disadvantage of this force? It is actually hard to predict the velocity, because once you have the electrodes here, the movement of the medium, as I mentioned, that will be something like vortex. But how we can calculate the velocity of this medium? Because the medium, of course, will drag your particle, and how we know the velocity of this particle is quite challenging. What's the application of the electroosmotic and electrothermal? One of the applications is micro pumps and also the micro mixer. You may heard that about the biofluid mixing, which we mix fluid or the biofluid within a small, let us say, small chamber or small microfluidic channel. We put two different electrodes with different polarity, and then we flow our fluid or our medium, and then we apply specific electric field with specific frequency, specific also amplitude, so it will cause something of mixing. So your biofluids will be mixed, so it will, at some point, it will become like more uniform. For example, you supply here one fluid, and you supply the other fluid from the other channel, and then by applying your electric field, it will look like mixing. And there is a lot of people working on this one. Micro pump is also something similar, but in this case, we'll just pump your fluid from one point to another point. Another application in edema treatment, usually in some cases where there is some liquid within your brain, they apply different electrodes at your head. And by controlling the electric field here, it might reduce the size or move this liquid from one place to another prior to extraction. Okay, so the fourth force is the dielectrophoresis. So this one is actually also different from the previous forces, that the movement, the particle that they will move is uncharged, which make this one of the best compared to the previous, which means that you don't need to do any treatment. So if you want to control or you need to move some particle, no need to do any treatment, because the particle, even if they are uncharged, you still can manipulate this particle. In terms of the electric field, in this case, we should have non-uniform. If we have uniform, it will not work. So we have to have non-uniform electric field. And also it is DC powered. So since it is can move uncharged particle, then how we can actually move the particle if they are not charged? The mechanism behind the dielectrophoresis is called particle polarization. So we need to polarize the particle actually. No need to put charge on the particle. No, we need to polarize them. And how we do polarize them? Usually the particle, for example, if you have a rod bacteria shape or maybe any other of particle, you will put them in the medium. And that medium should have conductivity and permittivity different from your particle. So let's say, of course, I'll explain more in this one, but there's a question here, what else DEB can do? It can do manipulation of bioparticle, as I mentioned before. So as I will go now into the manipulation. I will go more detail into what I mean by manipulation, which can be done by the DEB or the dielectrophoresis. So first, assembly and deposition. Let us say you have a mix of two bacteria here or two blood cells together. So how you can do assembly? You can do assembly, for example, you target one of these particles. Let's say we have this red, and we want to assemble the red particle across the electrode. So we apply electric field here with specific frequency, specific amplitude, and we can attract the red cell here to the gap between the electrode. So this is what they mean by assembly. Deposition is the same, but in this case, usually the deposit particle or the deposit ions will be on the top of the electrode. For example, here, if you have this mix of particle of ions, you can deposit specific ions onto the electrode. So this is what I mean by deposition. Another way of manipulation is the align and rotate. Align is if you have like, let's say, a molecule in the shape of a rod, okay, or in the shape of wires or in the shape of tubes. So you want to do a line. So again, you apply electric field here, and then because of the frequency or because of the intensity of the electric field, this particle will rotate. In this case, they will align in a way that they become parallel with the electric field. Rotation is something same, but in rotation, you need to control the rotation angle. So you might need to rotate by 90 degrees, maybe by 45 degrees. So this is the rotation. And all they can be controlled by the electric field. Trap and isolation, also another way of manipulation. Trap, you mean that we trap your particle on the top of the electrode. So I mean, this is at the state 0. This is example of trap. So we have, for example, here isolated the electrode, and this is the electrode that we apply electric field. So and somehow we can isolate or trap this particle on the top on specific area. Trapping means that you have a different type of particle or molecule, but you want to trap them in some place. Why we need to trap? Usually, before we do some analysis, let us say we take blood sample, and then we want to do analysis of a specific type of bacteria that we are looking there. So you might need to do trap so that you reduce, to concentrate that specific analyte that you target, you trap them in specific place so that you can easy for you to detect. Okay, lastly here we have the separate and sort. And separate and sort also same thing. For example, let's say you have a mixture of two different types of bacteria, but then you want to separate them. So you want to collect one sample with this bacteria, and you want to have another sample of the other bacteria. You can do this one with electric field, especially with the dielectrophoresis. You can apply your electric field across the electrodes, and then you flow your medium, and you can see one of the particles will be attracted to let us say, a high electric field here, and the other particle will attract to low electric field on the other side. So it will look at the end of your channel, you can get your bacteria separately. You flush them all together, and then you get each one in different outlet. Okay. If I want to compare the manipulation of particle with other mechanism or with other methods, Of course, we have a lot of methods like based on optical, microfluidic, mechanical, magnetic, and the electric field, which is the one that our topic today. I mean, we can control in different ways. For example, the controllability, the operation, the efficiency, cost, damage. So we can see here the way or the method that use electric field for the manipulation of bioparticle is first strong in terms of controllability. We can control them easily. All you need to do is for control your electric field, you control your frequency, control the permittivity, conductivity, your medium, and then you can get your cells somewhere. In terms of operation, it is easy. All you need is just function generator, and you need your electrode designed in a specific way. So the setup is easy. Also can be done in room temperature and doesn't require any complication. And efficiency also, the efficiency can be high if you correctly control the electric field. Then you can get high efficiency in terms of separation or whatever. Also cost low, and the damage is slight. Okay, so damage is one of the very important things, because in some case, after you do your manipulation or after you do your separation of your particle or your cell, you want to make sure that there is no damage to your cell or to your molecule, which is very important. And because some method, they will destroy your cells or your particles, so you cannot use them after that for any further analysis. But also need to make sure here you apply the specific or the what they call the good electric field. Otherwise, you will burn your electrodes or your cell. So we know that the dielectrophoresis, and we know the forces that can be generated by the electric field. So let's me now talk about the theory. What's the theory behind this, or how this actually particle move? What's actually the mathematical equation to do that? And before that, let me just give you this schematic diagram showing the system. We have here, for example, substrates, and we have here two electrodes. This is the simplest form of this particle manipulation using the dielectrophoresis or using the electrophoresis. We also have a function generator to generate your signal. We have also the switch, which means whenever you want to do some assembly or manipulation, you just switch on off. And you have, for example, your particle here. This is the droplet. For example, if you do this one in a static way, but some people, they do it in the microfluidic, so like real time. And then your particle usually, or your molecule, will be suspended or dispersed within your medium. So it will be like distributed randomly. When you switch on your switch, so usually there will be something will happen. In this example, I just give an example with some tubes. And usually when you apply your electric field, then the tubes will be formed across the electrode. This one also can be used in the fabrication or the deposition of thin films that use it for biosensing. So this one just a picture of one of the experiments I have done before. So you have just to connect your electrodes, and then you put your droplet here on the top of the electrode, and then you apply electric field, and then you can see there's things will happen there. Okay, so about the theory is actually simple. First, we have to have two electrodes, and the two electrodes must be different, must generate non-uniform electric field. So in this case, we have here particle 1, and we have here particle 2. And we have also the electrode, which is needle electrodes, and in the bottom here, we have just flat electrode. So let us see now what will happen. This is two particles. So one of these particles actually will move to high electric field, which is particle number 1. Whenever the permittivity of particle number 1 is higher than the permittivity of the medium, here will be medium. It's the water or ethanol or any other kind of solvent. If your permittivity of the particle is higher than the permittivity of the medium, usually your particle will move to high electric field. But if your permittivity of the particle is less than the permittivity of the medium, which is in the case in the black particle here, it will move to low electric field. So how we know this is low electric field? Because you see there is a high distance between the electric lines, but the distance between the electric lines here is very small. So this is very high electric field. So this we can explain in this way. So we have also different structure of electrodes, which is planar electrodes. Planar, like one electrode here, another electrode here, and then you put your medium on the top. So this is also the same. If we have like here in the rod shape particle, let us say a rod shape bacteria, for example, also same thing. There will be two forces acting on your particle, this way, this one and this one. And then the net force will be directed to your electrode gap, the gap between the electrode. So in this case also, we can sum the two forces together, and we can say that the net force that can be applied to this particle, if this force is negative, then the particle will move to the opposite. I mean, it will move away from the electrode. But if the force is positive, then the particle or your rod shape here, bacteria, for example, will move to your electrodes, or especially electrode gap. In general, it will move to the high electric field. And here we have high electric field. So this is basically the general theory. So later on, if you want to do some derivation and see what's the equation, the final equation will look like this. So the force that acting in your particle usually will be controlled by the particle itself. In this case, if you have spherical particle, then you have to know the diameter. So if your particle is small, then the force will be a little bit small. If your particle is big, then the force will be also high. And also it will control by the permittivity of the medium, which is one of the very important things that you know how to control your permittivity of the medium. But most of the medium, the permittivity or dielectric constant already known. So you can revert to the old chemical books. And also the third term that control your force is called the, I will come to this one, the last one I will say here, the electric field, which is the gradient of the electric field, which should be uniform. And then the third term here, which is RECM, called the real part of the gaseous Mozotti factor, which is a factor can be used to understand or to know. If you still remember, just in the previous slide, I mentioned that the permittivity is very important. So we have here two permittivity, the permittivity S and also the permittivity M for the medium. So we need to make the difference. We need to see, so is it will be positive or negative. If the permittivity of the particle is higher than the permittivity of the medium, then of course the CM will be positive, and after all the dB will be positive, which means that your particle will move to the electrode or to the high electric field. And the opposite case, if this term is negative, then your force will be negative and the particle will move away from the electrode. Okay, so then later on you can also calculate the velocity, your particle velocity. What's the velocity? You can just divide your force by specific fraction factor here. This fraction factor also depends on the type of your particle. And then if you want to know the total velocity of your particle, you need to add up the velocity of your medium. You add it with the velocity that be generated by the dB force and also by gravity if the particle is quite big. But in some cases, if the particle is quite small, it might be on some system that maybe you can ignore the gravity force. So this is basically the theory. There is very few things that you can control to get your force. You want to attract the particle, then try to make this is positive. You want to repel your particle, for example, to another place, then make sure or try to use medium, for example, with the low permittivity. I mean, you need all to control this one so you can decide you want to attract your particle or want to repel your particle. When we attract the particle, usually we will call it positive dB, and if we want to repel the particle, we will call the negative dB. So we have like two types, as negative dB and positive dB. So maybe I don't need to explain more here because this actually is obvious. We need to make sure that what's the permittivity and the conductivity. Yeah, okay. I forgot to mention that not only the permittivity is important, also the conductivity of the particle and also the conductivity of the medium. And sometimes also the particle is not like as simple as sphere. It's not like this. For example, in bacteria manipulation, we need to consider many things. The wall of the particle, membrane. Some particles have many membranes, for example, one or two, and also the cytoplasm, which is the core of your particle. Okay, so this one now it's more explaining the positive and also the negative dB. We have to make sure that about these two also, the conductivity of the particle, if it is less than conductivity of the medium, and also the permittivity of the particle is higher than the permittivity of the medium, we can get a curve like this one. So here is negative dB, which means your particle will repel, and here positive dB, which means that your particle will be attracted. So by controlling this, actually you can control what will happen in your system. Okay, now I will go to the more interesting part, which is the application in bioengineering. I mentioned a little bit few things, but here I will go more in details. Okay, number one, I will talk about very specific application, which we are doing here in KFUPM, which is enhance the biosensors performance in terms of sensitivity and selectivity. For example, we are working on bacteria sensing. We do concentrate low, for example, okay, let me explain that. why sensitivity and selectivity is very important. Sensitivity of any biosensor is very important because sometimes it is very hard to detect because the low concentration. Let's say you want to detect a specific molecule or specific cell or specific bacteria, but there is very low concentration of your molecule within the sample. When you drop the sample or you take your sample for testing, it might say that there is nothing detected, but actually there is things, but in small concentration. So maybe if we do some kind of concentrate, we concentrate that low amount of molecule into a specific place, and then we do the sense. So this is a way. Concentrate low concentration bioparticles for improved sensitivity. Another thing is the selectivity. Selectivity means what? Let us say you have a sample with tens of bacteria, but you want to detect only specific type of bacteria. So how will you do that? Okay, maybe you drop your sample and then your sensor gives you a reading, but you don't know which one of the bacteria is actually causing the response. So maybe you can do isolation before you do the sensing. You apply specific frequency, specific electric field that will only isolate that type of bacteria or will rebuild that type of bacteria, and then you do the sensing. So in this case, you do isolation before you do the sensing to improve the selectivity. I will explain about this more. But there is also other application of the dielectrophoresis or the electric field in the bioengineering. For example, one is the deposition of biosensing layer. Most of the biosensors usually they have a layer. Okay, so that layer, how we deposit? Usually there is a lot of methods now. For example, the drop casting, also the deposition. Also there will be like chemical deposition and physical deposition, many things. Spin coating. But also the electric field can play a role here in the deposition. Another thing is the trapping of biomolecules. This one, something similar to the isolate, so that we trap the molecule on a specific place to improve the sensitivity. Also, there's application of separation of cells. There's a lot of people doing blood cell separation. So, for example, they want to do some analysis on the cytoplasm, do some kind of analysis on specific cell. Okay, so they will isolate that cells from the blood, and they will remove the remaining of the sample, and then they will do Fox analysis on that one. So the separation in cell in general. Also, this one is play a very critical role now in cancer cells extraction. Also, we have the tissue engineering, which is actually very wide application, and also the concentration control, which is that we concentrate the type of bacteria or the type of particle before we do any further process. Okay, still have time. So for the bacteria sensing, most of you may be already familiar with this kind of methods. For example, the culture-based methods, the microscopic examination methods, enzyme substrate. There's many different sensing methods. But some of these methods usually require lab setup, so that you have to take your sample to the lab, and then you have to wait a few hours, maybe a few days before you get the results. And some might also be expensive. But and more important thing is this type of bacteria sensing methods usually is not real time. So you have to take your sample, you send it somewhere, and then you have to wait. Maybe let's say if you want to do these people who are working on the water treatment factory, or even just the normal water supply to the houses, they cannot just take samples every day to check if the sample or if the water is clean or bacteria container. So in this case, there is a need to do some kind of real-time sensing. So we have here a proposed one system that we are using. We apply the electric field, or we apply the dielectrophoresis in our system, that so we can have real-time detection. For example, if you can see this sensing unit, the thing is that in white here is microfluidic channel. So let us say we have an inlet. We put our sample here, or our water sample here, and the water will flow from the inlet to the outlet. But before the sample reach to the sensing electrodes, it will pass through another set of electrodes to do the concentration, which that I was just talking now. So we apply specific electric field here from, it will comes from a circuit unit with a specific frequency and maybe specific amplitude across the electrodes here. And then when the sample pass through the electrodes, it will do kind of isolate. So we isolate the bacteria that we are targeting. So let's say we target E. coli to check. So we apply specific frequency that actually the only E. coli can be response. And how we can adjust this frequency? We need to go to analysis the bacteria first. We need to know what's the wall permittivity, wall conductivity, membrane conductivity, membrane permittivity, and also the cytoplasm of that bacteria, and of course the size. So by doing some simulation, we can know at which frequency the E. coli, for example, can be isolated or can be directed to a specific direction. And then once the sample reach here, we already have that type of bacteria on a specific flow. And then we can take the reading and we can measure how many cells pass. And of course, the cell can be determined by the concentration of your how many cell. We can also play with the capacitance, for example, or the impedance. And of course, here the electrodes from electronic perspective, we can also apply, let's say, simple electrode capacitance, or maybe you can apply impedance spectroscopy method. But the main important thing that related to our talk here is what will happen here. This is the main thing, that we do kind of isolation first before we do the sensing. Okay, so I will give you here some example of some simulation. We took simulation of 3 different bacteria, which is, of course, the name of the bacteria is very difficult. So I made shortcut here. We have SA and SE, and we have the last one, E. coli EC. So we do some simulation. We see at which frequency this bacteria can be response or can behave differently. For example, I will just go to the E. coli because of the time. So for E. coli, at frequency below 14.5 kilohertz, it will have negative DEB force, which means at this range, the E. coli will rebel. I mean, it will move away from the flow. It will move away from the electrode. But at frequency from 14.5 until 50, almost 57 megahertz, at this range, the E. coli will behave like differently. Instead of rebelling from the electrode, it will be attracted. And also for frequency higher than 57, the bacteria will have kind of a negative DEB, which means will rebel again. Rebel, attract, rebel, something like this. So this is the way. And of course, let us say now we have flow, have these all 3 bacteria, and we want to separate the SE bacteria. So of course, what I will do, I will apply electric field with the frequency between 30 megahertz to 57 megahertz, because at this frequency only SE bacteria can be repelled, while the other can be attracted. So the whole bacteria will be attracted this way, while the Staphylococcus epidemic bacteria will be repelled. So that is how we do it. We take the whole spectrum of the whole frequency for different bacteria, and then we see. In some cases, it will be a little bit difficult. For example, if you want to isolate the E. coli, at this frequency, still SA bacteria will be there. And also here, because at this frequency, usually will be shared. It will share some frequency with the other bacteria. So in this case, maybe we can do 2 levels of isolation. And this, okay, so how we got this curves? We got this curve is by applying a simulation. We need to consider many things, actually. The bacteria, I mean, all the layers of bacteria we need to include. For example, the wall, the membrane, the cytoplasm, and the properties of all these 3. Whenever you make your model is more complex, you can get better or a good result that usually will be can be validated experimentally. Okay, another simulation and experimental result also. We apply here into microfluidic channel. We apply different type of bacteria. Here we have 3. Same thing that I just explained now. And then by applying specific voltage, and also not only the frequency, by the way, not only the frequency can be used to control the manipulation, also the electric field. Because in some case, if you use electric field low, all bacteria will be like same together. There will be no separation. But in some case, if you use higher electric field, for example, in this case, if you can compare these 2, we have here 1 volt. Of course, the same flow, which is 100 micrometer by second, but the voltage is different here. 1 volt, here 10 volt. So in 1 volt, nothing happened. Like all the bacteria remain together. They came to the separation electrodes, nothing happened. And then for the sensing electrode, they all go like turn on the top of it. So also there is nothing will happen in the sensing. But let us say you apply 10 volt peak to peak, for example. What will happen here? What will happen here is the bacteria with the bigger size. If you still remember that the DB force usually it will depend also on the size of your cell or your particle. The force, the particle or the cell or the bacteria cell with the high size, usually it will experience strong it will experience strong DB force. So what will happen? It will happen something like this. I think this is the E. coli because it will have bigger size, so it will repel to here, and only the SE bacteria will pass through the electrode. So in this case, if we took the reading, for example, the capacitance of these two electrodes only will give us the capacitance on this specific type of cell, while the other thing that already we made sure that they move away from the sensing electrodes. This one, same as this one, but in this case, we apply fast medium flow. The flow here, like 500 micrometer per second. So in this case, because the flow is very fast, so the electrode were unable to do strong separation. So the bacteria that pass through the electrode, only the E. coli, while the other two, they remain on the other side of the electrode. So you can also control the flow of the medium. Here we have some experimental result. This one, Electrokinetic bacteria. We try to apply electric field and see is it possible really to attract or to concentrate bacteria cell with an electrode. You can see here at 0 volt, there's only a few cells. Whenever you increase the amplitude, you can see there is more cell is being attracted to the gap. So this is ITO electrodes. This is glass substrate. So this is the gap between the electrode. The size of the gap here is 50 micrometer, 50 micrometer. And also here, in terms of accumulation or separation, separation, we have here a mixture of E. coli and also Bacillus. Also, we apply here at different frequency. You can see there's different shape, or mean that the bacteria that distributed is actually different at different frequency. I think there is something here accumulated at the edge of the electrode. You can see there is a darker here area. We expect this is the E. coli have been accumulated here, while the other bacteria remaining distributed in the medium. Okay, so this is about what we do actually here. I mean, one of the projects that we are working here at KFUPM. So now I will give like very brief on other applications, not the bacteria separation or manipulation. So one of these is deposition of biosensing layer. Actually, I mentioned before. In this case, we use the electric field or the dielectrophoresis to do the deposition. For example, the normal way of deposition, as I mentioned before, is like spin coating, drop casting, normal coating, or maybe CVD chemical deposition, or maybe also bath deposition. Many methods actually. So one of these methods, let us say that you want your sensor to be very small, or the dimension of your sensor is very small. Like in this case, maybe only 35 micrometer the gap. So in this case, very difficult to do the coating. So maybe you can apply the electric force to do the deposition. So you apply your electric here across the electrode, and then you would drop if your thin film materials, for example, in this case, I think here gallium nanowires. And then before you do before you apply the electric field, maybe you do your treatment before, and you attach the abatement that you use or whatever, you attach them to your nanowires, and then you apply the DB so that you can have a very uniform thin film or very uniform, let us say, sensing layer. This one also can be used if you have ID electrode, or also if you have just normal pair of electrodes. And this also can be used also in transistors. And there is a lot of application of field effective transistor that are sensors that are based on transistors. Also, you can do the deposition of your channel here using the electrophoresis. So this one application. Another application also trapping of biomolecules. In some case that you want to trap your molecule in a specific place so that you can do further analysis or further detection. In this case here, for example, we have the BSA, which type of protein. So for example, if you do trapping, you can trap in different areas. So if you apply a negative electric field, so you can trap the molecule on the top of the electrode. Okay, but if you apply a positive DB, then you can trap them in between, so like in the gap here. This is also based on your application or your target. Another also research here from other people who do kind of trapping molecule also between into holes. Okay, they prepare specific type of electrode, and then they actually there was a very significant difference in the on the sensitivity of the for their device. So the trapping of nano-sized biomolecule on plasmonic nanoholes array. So they have an array of nanoholes, and then you can see here in the result, if you look at this at 1000 B mol per microliter, but this one at 0 volt. So the sensitivity or the system is very low. I mean, if you see here the triangle, red triangle. But then they repeat the same experiment, but they apply electric field here from the top electrode to the bottom electrode. Again, sorry, actually, this is the electrode and this is the other electrode. When they apply the electric field of 5 volt, the sensitivity or of their system jump from almost here 0 or maybe 0 point something to 5. And since because they are using the plasmonic system, so of course that the shift will be in the peak shift. So the peak shift become higher, so the detection can be very clear just by trapping holes. Just a little bit. Okay, another application is the separation of cells, red cells. If you have also blood, if you can see here the result, they have blood, but then they apply specific electric field with 20 volt peak to peak to 100 megahertz. So they can separate the cells, the red cells, and they keep the plasma in the middle. So this is also another application. Also for tissue engineering, you can use the dielectrophoresis also to stimulate the wound healing, especially for people who suffer from diabetic foot ulcer patient. You can apply also you put electrodes near to the wound, and then you can apply electric field. It will stimulate the healing process. Yeah, I think maybe we can just go again fast. Of course, this is maybe until now so nice, right? But what's the challenge? There is a lot of challenge actually in the whole system. For example, one, controllability, very difficult to control your system. Also, we have in some cases this is very important actually. Joule heating. Sometimes will be a heat will be in your medium, and that heat it might cause cell damage. So you need to make sure what is the permittivity or medium. Control the permittivity and conductivity is very important. Okay, reproducibility. This one for the sensors. So sometimes if you do the deposition, you need to do it again. So you make sure that the output will be same, which is very important actually for the biosensing. Okay, and this one also another thing. If the deposition of your biosensing layer is a mixture of more than one material, also you need to do a controlling deposition. So I think that's all for future and outlooks. Maybe you can use the DB for the response of new structural materials, because some people they just apply the deposition for specific types of materials. So maybe we can also try to explore new materials. And also the fabrication bioparticle sensor using composite nanomaterial, which I just mentioned now. Most of the sensing layer usually will be only one material or two or composite of two material. So we need to explore how we can do that with the dielectrophoresis. And that's what we are doing now. Doing the DB in water treatment or sensing the bacteria in different water samples. So that's all from me. Thank you for your listening.
Well, thank you very much for the excellent journey. You took us in journey through all the basics to applications to the challenges. Very nice. Maybe we have time for a couple of questions. Please.
Thank you for a very interesting presentation. I have two questions. First question about the safety for the device, especially for the one that used to detect the E. coli in home or to get the real time. And since it's relying on the electrical signal, I'm wondering if it's safe to not induce any shock to users.
Okay, for the DB, actually, the voltage that we apply it is very low. It's from like we use 1 volt, 10 volt. Even in our experiment, the maximum we use 10 volt. So with an AC signal with this range of frequency and amplitude, it is not that like difficult or harmful or something. And of course, if we want to implement the system into, like, let's say, the water pipes, of course, it will be like packed and will be not will be like exposed to the air, or this, of course, will cause problems. So if we pack the device, should be no problem. But in terms of the thickness that we use, it's very low, especially the one for the separation.
For the second question, it's about you mentioned, I think, in slide 18, microfluidic systems that before the detection of the E. coli, you isolate the targets.
Yes.
Organisms, the thing. So how about the concentration of the low concentration to concentrate the microfluidic? How you concentrate if you have like very low concentration?
Oh, you mean for the testing or for the real application? I mean, if you do the testing, this will prepare our sample in lab with different concentration. We just, for example, we prepare our bacteria sample, and then we will add the medium in different concentration, so that the concentration of the bacteria itself within the medium will be different. And this is very also important to do some kind of, let us say, experimental and simulation for different concentration. Because if the bacteria is small, of course, the reading at the end, I mean, at the sensing electrode will be very small. But if the concentration is high, of course, the capacitance will increase based on the concentration. But how we control this, we do it in lab. I mean, for the just research purposes. But later on in the real application, we will never know the concentration. Only the device will tell us. Or maybe we can have another method for verification. So we do our testing here, and then we verify using other methods as a reference.
So the device will be designed based on the certain limit of detection, let's say.
Okay, since it is real time, so maybe because I know in sensors, people usually they scare of saturation. So let's say maybe your sensor would be saturated at specific value. But in our case, since it is real time, so the water will keep flowing. So maybe now you measure this type of fluid, then maybe after a few seconds, already your medium already passed away. So maybe the reading is from another sample. So it's like real time. So we are not concerned about this, the saturation of the sensor.
Thank you.
Any other question? Yes, please.
Can you go to the first simulation? Thank you, Dr. Abdullah, first for the analysis.
This
Yes, here. First question, what will happen after 10 gigahertz frequency, for example? Have you tried higher frequencies?
as simulation, yes, it will continue the negative.
I mean, the graphs here. Yeah.
You mean, okay, let's
It's
say,
up to 10 gigahertz, right?
yes. I mean, here you just need to follow the curve, where it will go. For in some case, if it is, for example, in our case here, we are only care about the real part, which is the black curve. So the black curve here will continue below 0.0 if we extend the simulation behind this frequency. So which means that the bacteria all still will experience negative. So they will rebuild. So it's like not significant to do it.
So the imaginary part here is not important, right?
Yeah, not important.
So why would you
You have to know, because in certain way, some people they use, for example, this one only like one wave. Maybe some people are concerned about the three phase. They use like not only two electrodes, they use, for example, three. So in that case, this one will be significant. We have to do, they call it traveling wave, DEB. This one is for the basic DEB. If you're using the traveling wave dielectrophoresis, then you have to concern about the negative, the imaginary part. And also, okay, I need to add also, the imaginary part also, it will help us to determine the shifting. So for example, if you take this peak, usually at this frequency, that will be the shift. So it will give you the peaks at where the
Are you interested to find the frequency that will give you the maximum or the real part and the imaginary part as well, or the minimum ones, or the opposite? So if you are interested in that, then you can plot the phase. So the phase will give you very important information.
Yeah, we might also try to that one. But basically here, we're doing the real part just to know where is the positive and where is the negative. And the imaginary part, we need to know where is the shift. Where is the shift?
I was also confused by the label of the y-axis, because you are putting the real part, and in the legend, you put the real and the imaginary as well.
Okay, yeah. Sorry about that.
Thanks.
So I need to fix the
Thanks.
y-axis.
Any other quick question? Yeah, last question. Maybe we can take.
After applying the DEP, did you check if the surface charge of the molecules changed?
Okay, for DB, actually, we are not concerned about the charge at all. All we need to make sure is the polarization, because the particle itself will polarize. So we haven't checked. If, for example, if we are doing cell, so maybe after we apply, the cell will be attached to the electrode, for example, or maybe it will repel away from the electrode. So in terms of like checking, we are not concerned for the DB itself. But if we are using the electrophoresis, then one maybe it is very important to make sure of the charge, because this one just based on polarization.
Okay, thank you very much. Sorry. Sorry, yeah.
I thank you very much for the nice presentation. My question is that this method depends a lot on the ability to separate bacteria in a specific region, right? Because naturally we know that bacteria concentrate, like different bacteria exist in a specific place. So if you're looking for a specific one, that means you need a method. You have to devise a method that can separate them so that you can isolate the specific one you want. So it means most of the work is in the isolation of the bacteria.
Okay, yeah, good question from Dr. Abdulhameed. If you're concerned about our lab, I mean, for example, let's say there will be a lot of processing, medium process. So you have to process, you take a water sample, you need to process to separate all type of bacteria. If you want to do this one in the lab, to do the experiment, to just make sure that what frequency is good for what bacteria, this one we have to do it. But in our lab, we already have samples for different type of bacteria. But if you want to do this one on your real time, let's say we already have the device, then actually the device it solves this problem. So you don't need to do any processing. You don't need to do the sample processing. It solves this challenge, because in other methods, let's say PCR or any other detection method, you have to take the sample and do some kind of treatment. So you make sure only that bacteria that you want to sense is there. But for our method, it's just you need to do separation before and at the same time by applying the specific frequency that only will isolate that type of cell. So you don't need to do this process at all.
Okay, excellent. Thank you so much. Thank you for